Hello again. So I took the same measurements you did today in class. I hung a mass from a spring, and I measured the length of the spring in this column. I'll call that L0, meaning at time equals 0. And then I measured, put a weight on it, and I measured the length after it stretched. I called that L final. The mass that I put here. The graph we're supposed to make is supposed to be the restoring force versus the displacement. In class I called it delta x. I'll just leave it x. And so the restoring force, we know that at this point at which it's stretched, the force of gravity, which I can get from the mass, and the restoring force in the spring must be the same size. That's why it's not accelerating. So since we're supposed to have a force of gravity, which I'm going to say is the force that restores in the spring, and these are masses, technically I need to convert that to what the force is. And we showed that in class today. We said 436.3 grams. I need to change that to kilograms. Let's see, 1,000 grams is a kilogram. And on Earth, 1 kilogram weighs 9.81 newtons. And if you calculate that out, you get 4.2, and I'll say that's 3 sig figs, 4.28 newtons. So this column here is a calculated column of data, but that's okay. You're supposed to have one sample calculation, which I've done, and the rest I'll just do on my calculator. Let's see, so this column is 4.28 newtons. This column here is 5.71 newtons, and this one's 9.81 newtons. So now I have my data. I'm going to graph the weight, which is the same thing as the restoring force, versus the stretch. And I'll do that here. So I've transferred the data here onto this graph so we can make a graph together. In chemistry, we were supposed to have learned that graphs are supposed to be a full page. They have to have a title. So the title is, in this case, what we're measuring, and that's a good enough title for now. So this axis here is the restoring force in the spring. That'll be in newtons. And this axis here is going to be the stretch, and it looks like those units are in centimeters. So we're going to call this graph the force versus the stretch, and that's a good enough title for right now. So we are supposed to make the axes such that our data is spread out. So to do that, let's see, I have 1, 2, 3, 4, 5. I just decide to make marks every 5 to give myself a ballpark of where I'm at. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I do the same thing here. 5. Okay, so it looks like, if that's focused, on the y-axis, or the vertical axis, I have to go from about 4 to about 10. If there's no weight on the spring, the stretch should be 0. So I'm going to include 0, 0 as a data point and not put any kind of break. So I have to go basically 0 to about 10. So let's see, that's 10, that's 20, that's okay. So I can't go by ones because then I would only use this much of the graph paper. If I went up by 0.5s, I'll use this much of the graph paper. So if I went up by 0.2s, let's see, that'd be 0.2, 0.4, 0.6, 0.81. So that'd be 1, 2, 3, 4, 5, 6. Okay, so 10's not going to fit. So it looks like 0.5 is the best I can go up. We're not going to mess with deciding whether or not horizontal or vertical is the best way to put the page. And we'll just kind of do it this way. Now, in college, they might ask for that, but that's okay here. So 0.5s. That would make this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that this distance is a little more than half the page, and that'll be okay. On the vertical axis, or the horizontal axis, I have to go from 0. It looks like I got to about 35. So 10, 20, 30, 40. I have a feeling if I go by 2s, that gets me out to here. If I go by 1s, it'll be 5, 10, 15, 20, 25, 30, won't fit. So 2s is the best I can do. 2, 4, 6, 8, that'd be 10. 2, 4, 6, 8, 20, 30, 40, and that's good enough. So let's put our points. The first point is 11.6, which is somewhere in there. Now you'll notice this goes up by 2s, so 11 is about there, 11.6 is somewhere a little past. It's the best I can do because I can only really see the ones place here. So I'll guess 11.6 is about there, and 4.28 looks like it's about 4.5. So even though this axis is going up by ones effectively, which means I can get the tenths, I'll call this about 4.3 and say it's about there. And here's my first data point. Okay, 4.3 and okay. Make a nice big data point. My next data point is going to be 17. Let's see, that's 12, 14, 16. So 17's in the middle, about. And then I need to go up to 5.71. So if I come up here, 5.5, 5.7's right about there. The next point would be 33.5, which is about, here's 31, or here's 32. So here's 33 up here. And on the other axis, I need about 9.8, which is near 10, right about there. And there's my data. Now, hopefully that data goes through 0, 0, and to me it doesn't look like it does. If it doesn't go through 0, 0, then don't make the line, the best fit line, go through 0, 0. And we'll talk about what that point must mean, because if you think about what it means when there was 0 stretch, there was already some weight on it. We'll talk about what could have caused that. What that implies is all of the data is shifted up a little bit so that my line is up here instead of down here. That's called a systematic error, where there's a consistent shift. So I won't worry about that right now. The general pattern does look like it's linear. And so let's find the slope. To find the slope, you do not use your data. Do you remember this? You take 2 points from your best fit line. Let's see, I'll just take 2 random points. So there's one, and here's one far away. And I'm going to take them far away because I'm going to do a subtraction and I don't want to lose any sig figs. I'm not going to hope for ones that go through the corner, because you kind of say, oh, that's pretty close, and then it's not close enough, and you just kind of force it to be in your mind. I'm going to draw a little box here to give myself a sense. It's right on that line, and it's down here. Okay, just to kind of find my points. You don't have to do that. So, and here's the second one. It was just past this line and just past that line. So, how do you show your work when you find the slope? Well, let's see. I'm going to go the slope, which in science they use the letter K, is the change in force over the change in stretch, or force number 2 minus force number 1, and x2 minus x1. So let's plug some numbers in. Force number 2, based on what I picked. So that's 10. That was 11. That's 12. This axis here should have a tenths place. So I'm going to say 12.0. Those are newtons, minus, looks like 2.0 newtons. In the denominator, I'm going to have, let's see, that one looks like it's just past. Actually, that one up there was a little bit past, but I'll do it this way for now. That's about 42. It looks like one's place there, so I'll say 42 centimeters. And then this one right here looks like it's about, well, let's see, the nearest that would be is maybe 2 centimeters. That makes the numerator 10.0 newtons and the denominator 40. Well, I'll put a little mark there to remind myself that's the ones place, centimeters. Okay, and if I go 10 divided by 40, that's 1/4. So let's see, that's going to be this slope should be with 2 sig figs. Let's see, 0.25 newtons per centimeter. So the equation of this line is the force equals 0.25 newtons per centimeter times the horizontal axis, which is x, plus this shift of about 2 centimeters, which is a problem. Hooke's law is really F equals kx. In other words, the stretch of a spring is linear with some proportionality constant. In fact, for a spring, that constant is actually called the Hooke's law constant. When you buy springs, you look it up and see what the value of the spring constant is. It basically tells you how stiff the spring is. If it was more newtons per centimeter, that'd be like a stiffer spring, and if it was less newtons per centimeter, and so, for example, a car doesn't want a lot of stretch when you go over a bump, but a ballpoint pen spring wants to be easy to push in. Okay, so you learn a lot about springs here. This is just a reminder of all the little subtleties of how you make a graph and write an equation for our class.